Welcome back to the deep dive. When most people think about machine learning, they picture like a student learning with an answer key, right?
Exactly. Like they see 1,000 pictures labeled cat, and boom, they learn what a cat looks like. That's supervised learning. You know the target.
Right, you have the answers beforehand. But what if you didn't?
Imagine taking that same student, dropping them into, say, the Library of Congress, and telling them, okay, organize all of this, but no labels, no Dewey Decimal System, nothing. Just find the structure.
And that's our mission today. We're diving deep into unsupervised learning, UL for short. It's all about how algorithms find hidden patterns, how they turn raw, messy, unlabeled data into something useful.
Yeah, purely by looking for the inherent structure. No hints allowed.
The defining thing about UL is that total lack of a dependent variable. There's no U value you're trying to predict.
The algorithm just gets the inputs, the features, and it has to figure things out on its own. Find common ground, find relationships. It's basically a core exploratory data analysis.
And I think it's important for you listening to realize UL isn't just some, academic exercise. It can be the main goal. Maybe finding unknown customer groups.
Sure, market segmentation.
Or, and this is really practical, it can be a step towards another goal. Like you use UL first to clean things up, find some structure.
And then you feed that better structured data into a supervised model down the line. It's often a crucial pre-processing step.
Okay, so if there's no specific right answer to aim for, what are these algorithms actually doing? What are the main jobs of unsupervised learning?
Well, you can boil down most UL activities into two fundamental missions. Both are really key when you first encounter a new data set.
Okay, what's the first one?
First up is clustering. Simple idea, really. It's about grouping things together. The basic rule is things inside one group, one cluster, should be more alike than they are to anything outside that group. You're essentially asking the data, what are your natural categories?
Finding the natural breaks in the data makes sense. And the second mission. That deals more with just the sheer scale of data, right?
Exactly. The second core task is dimensionality reduction. This becomes absolutely vital when you're dealing with data that has, say, hundreds, maybe thousands of different features or columns. The goal here is to kind of compress that massive set of features into a much smaller, more manageable set of variables, but crucially, ones that still capture most of the important information from the original set. It's like smart compression for statistics.
It really is a broad field. I mean, our sources even mention 4 slightly wider categories, right?
Yeah.
Clustering and dimensionality reduction are the big two. But also anomaly detection and then specific methods for neural networks. It just shows how fundamental UL is becoming. All right, let's dig into clustering a bit more. How does an algorithm, just looking at raw numbers, decide what's similar enough to group together?
Conceptually, the goal is pretty straightforward. You want to minimize the differences within a cluster, make them tight, cohesive, and maximize the differences between clusters, make them separate. But, the idea of a cluster itself is a bit fuzzy. Is it a dense ball of points? Is it a long, snaky chain? Because there's no single definition, we end up with lots of different algorithms.
Okay, so what's the go-to algorithm, the one people usually start with?
Oh, that's definitely k-means. It's everywhere. With k-means, you actually have to tell it up front how many clusters you're looking for. Let's say you decide on DOCL clusters. It then shuffles the data points around between these dot clusters, trying to make the variance, the spread, inside each cluster as small as possible. It works well, but that need to pre-specify dollars is a big condition.
What if you don't know how many clusters there should be? Or if data's kind of messy?
Then you might look at something like DBS-scan. That stands for Density-Based Spatial Clustering of Applications with Noise. Quite a mouthful. DBS-scan basically looks for areas where data points are packed closely together. And the clever part is, if a point is off on its own in a sparse region, DBS-scan doesn't force it into a cluster. It just calls it an outlier, or noise.
Oh, that sounds really useful for real-world data. It's never perfectly clean. What about methods that help you visualize the structure?
Right. You're probably thinking of hierarchical clustering. This approach doesn't just give you one set of clusters. It builds a whole hierarchy, like a family tree of nested groups. You often see this shown as a diagram called a dendrogram. It's great for exploring because you can look at the tree and decide later how many clusters make sense by sort of cutting the tree at a certain height.
Interesting. Now, before we leave clustering, association learning. Sometimes it feels separate, but it fits under UL, doesn't it?
Absolutely. It's unsupervised because there's no target variable. Association learning isn't about grouping observations so much as finding relationships or rules between items. The classic example is market basket analysis, what items are bought together. Algorithms like a priori find rules like if people buy A, they often buy B based on metrics like support, how often A and B appear together, and confidence, how likely B is given A.
Okay, makes sense. Now, you mentioned k-means, DBS-can, hierarchical. Many of these rely on distance.
Right.
If my data is numbers, okay, I use Euclidean, the straight line.
Right.
Or maybe Manhattan, like city blocks.
Right.
But what if my features aren't numbers? What if it's text? How do you measure distance then?
That's a really crucial point. You have to pick the right distance metric for your data type. For text, especially high-dimensional text data from things like document analysis, we almost always lean towards cosine distance.
Okay, why cosine distance for text? Why not just Euclidean?
Because Euclidean distance measures the actual geometric distance, the magnitude. Two documents could be far apart just because one is much longer than the other, even if they talk about the exact same thing. Cosine distance, on the other hand, measures the angle between the vectors representing the documents. It cares about the direction, the topic distribution, not the length. So those two documents on the same topic, their angle will be small, close to zero, even if their lengths differ wildly. It captures thematic similarity better.
Got it. Topic, not length.
Exactly. And there are others too, like Levenstein distance for comparing strings, how many single character edits to change one word to another, or Hamming distance for strings of the same length, counting positions with different characters. The takeaway is huge.
Yeah.
Your choice of metric fundamentally changes what the algorithm sees as similar.
Okay, let's switch gears to that second big mission, dealing with massive data sets. It's like clustering gets hard in high dimensions. So if I've got data from, 100 different sensors streaming in hundreds of features, can these clustering methods even cope?
That's where you run smack into what data scientists grimly call the curse of dimensionality. It's not just hard, it can completely break things. When you have too many dimensions, the space becomes incredibly sparse. Everything starts to look equally far away from everything else. Those nice, intuitive ideas of neighborhoods or closeness just dissolve.
So the algorithms lose their bearing.
Pretty much. They become ineffective, and worse, your risk of overfitting any model you try to build later just skyrockets because you can always find weird, spurious patterns in all that empty space.
So dimensionality reduction isn't just nice to have, it's often essential. We need to project that complex structure down into fewer dimensions, maybe just 2 or 3 for visualization. And this whole process hinges on finding these hidden latent variables.
Precisely. Latent variables are the underlying concepts or factors that we can't directly measure, but we think are driving the patterns we do see in the data. Like in market research, you might measure 50 different buying behaviors, but the underlying latent variables might be things like price sensitivity or brand loyalty. We infer them.
And the absolute workhorse algorithm for this is principal component analysis, PCA. What's its main goal beyond just, making the table smaller?
PCA's core objective is to distill a large set of variables down into a smaller set, the principal components, in a way that retains the absolute maximum amount of the original data's variance or information content. It's about simplifying while losing the least amount of signal.
And how does it actually do that compression? What makes the output so useful?
It constructs these new variables, the principal components, by taking linear combinations of the original input variables. It does this step by step, each time creating a new component that explains the largest possible chunk of the remaining variance. But here's the really clever, strategic part. These new components it creates are mathematically guaranteed to be independent of each other, uncorrelated.
Okay, hold on. That independence, why is that such a big deal?
Because it tackles a massive headache in modeling called collinearity. That's when your input variables are highly correlated with each other. Many standard models, like linear regression, get very unstable or even fail completely when faced with collinearity. PCA cleans that up. By transforming the data into a set of independent components, it makes the data much better behaved for feeding into subsequent supervised learning models. It improves stability.
Okay. So you get statistical benefits.
Yeah.
But there's always a catch, right? You mentioned a trade-off.
There is. The big one is interpretability. You lose it. Your first principal component might be, 0.6 times sensor A minus 0.3 times sensor B plus 0.1 times sensor C. Mathematically, it captures the most variance, but what is that combination? It doesn't map neatly back to a simple, real-world concept you can easily explain to a manager or a client. You trade clarity for mathematical purity.
Right. So PCA maximizes variance, creates independent components, but they're harder to interpret. What about independent component analysis, ICA? How is that different?
ICA has a different goal. While PCA looks for directions of maximum variance, ICA tries to find underlying components that are not just uncorrelated, but statistically independent in a stronger sense. It's focused on source separation. Think of the classic cocktail party problem. You have multiple microphones recording several people talking at once. ICA tries to separate those mixed signals back into the individual voices, assuming the original voices were independent sources.
Interesting.
And often, ICA actually uses PCA as a first step. It might run PCA first to reduce dimensions and remove some correlations, making the data cleaner before it attempts the harder job of finding the truly independent underlying sources.
Okay, let's jump into the neural network world. Usually we think of training them with huge labeled data sets like ImageNet. But how do neural networks leverage unsupervised learning? How do they cluster or select features without that external feedback loop?
They often rely on learning rules that don't need an explicit error signal from a label. A key idea here is competitive learning. Imagine you feed an input pattern to a layer of neurons. In competitive learning, all those neurons effectively compete to respond to the input. The neuron whose current weights are already closest to the input pattern wins.
Okay, a winner-takes-all situation.
Sort of. The winning neuron, and maybe its immediate neighbors, gets to adjust its weights, moving them even closer to that input pattern. The losers don't change, or change very little. Over time, different neurons specialize in responding to different kinds of input patterns.
And this competitive idea is behind self-organizing maps, or SOMs, also called Cajonan maps.
Exactly. SOMs are fantastic for visualization. They take high-dimensional data and project it down onto a low-dimensional grid, usually 2D, but here's the key. They do it while preserving the topological structure of the original data. Think of it like creating a flat map of a country. Cities that were close together in the real world should end up close together on the map. SOMs do that for data points. If 2 points were similar in, say, 50 dimensions, they'll end up near each other on the 2D map.
Very cool for exploring data. And then there are autoencoders, AENCs. These seem to be everywhere in deep learning for UL right now.
They really are. Autoencoders are primarily used for learning efficient representations or codings of unlabeled data. They have this characteristic hourglass shape. There are 2 main parts. First, the encoder network takes the high-dimensional input data and compresses it down into a much smaller, lower-dimensional representation, often called the latent space or bottleneck layer. Then the second part, the decoder network, takes that compressed code and tries to reconstruct the original input data as accurately as possible.
Wait, so the goal is just to get back the same thing you started with. What's the point?
The magic is in that compressed code in the middle. Because the network is forced to squeeze all the information through that narrow bottleneck and then reconstruct it, it has to learn the most important, most salient, non-redundant features of the data. By training it to minimize the reconstruction error, the difference between the input and the output, you force that middle layer to become a really powerful, compact representation of the data's underlying structure. That learned code is often way more useful for downstream tasks than the raw input. It's like learning the data's fundamental language.
That makes sense.
Yeah.
Learn the essence by forcing compression. We should probably also give a quick mention to restricted Boltzmann machines, RBMs. They were pretty foundational.
Definitely. RBMs are a type of generative neural network, meaning they can learn the underlying probability distribution of the data and even generate new samples. They have 2 layers, a visible layer for input and a hidden layer for features. They're restricted because connections only exist between the layers, not within a layer. They learn by trying to reconstruct the input data, similar in spirit to autoencoders, but the learning algorithm, often contrastive divergence, is quite different and notoriously a bit tricky to get right. They were crucial stepping stones in deep learning history.
Okay, we've seen UL as powerful for finding structure, reducing dimensions, learning representations, but we've skirted around the elephant in the room. How do you actually know if your unsupervised model is any good? Without ground truth labels, how can you possibly measure accuracy?
You've hit the nail on the head. This is the single biggest practical challenge in UL. You run k-means, it gives you 5 clusters. Are they the right 5 clusters? Are they meaningful? It's tough to say definitively. Since we don't have accuracy, like in supervised learning, we have to rely on other ways to evaluate, generally falling into 2 camps.
Okay, what's the first approach? Using just the data itself.
Right, that's internal validation. Here, you use metrics calculated only from the input data and the cluster assignments the algorithm produced. You're basically measuring how well the clustering fits the data's own structure. We look at things like cohesion, how tightly packed are the points within each cluster, and separation, how far apart are the different clusters. The most popular metric for this is the silhouette score.
The silhouette score, right? It goes from -1 to 1. Can you break down what those scores mean?
Sure. A score close to +1 is great. It means your clusters are dense and well separated. Points are clearly matched with their own cluster and far from others. A score around 0 is... It suggests clusters might be overlapping or points are very close to the boundary between clusters. It's ambiguous. And a score near -1 is bad news. It means points have likely been assigned to the wrong cluster. They're actually closer, on average, to points in a different cluster than their own.
Okay, so internal validation gives you some clues. What's the other way? External validation. Sounds like bringing in outside help.
It kind of is. External validation requires some form of external benchmark or information that wasn't used to build the clusters. You compare the clusters your algorithm found against a pre-existing known set of classes. Maybe these known classes came from expert manual labeling or some other established process. You then use metrics to see how well your algorithm's clusters map onto these external classes. If there's a strong correspondence, you gain confidence that your unsupervised model found meaningful structure.
Got it. Using outside info to check the results. Now, one last crucial application we touched on. Anomaly detection. Finding the odd ones out.
Yes, a really important use case for UL. Anomaly detection is all about identifying those rare items, events, or observations that are significantly different from the majority of the data. Think fraud detection, network intrusion, manufacturing defects. Since anomalies are, by definition, different and rare, unsupervised methods are often good at spotting them because they don't fit the common patterns the algorithms learn.
Are there specific algorithms good for this?
Definitely. Isolation forest is a very popular one. It's clever. It builds random decision trees. The key insight is that anomalies, being rare and different, tend to get isolated in the tree structure much earlier with fewer splits than normal data points. So you look for points with short average path lengths in the trees. Another well-known one is local outlier factor, or LOF. It measures the local density deviation of a data point with respect to its neighbors. Points in much sparser regions than their neighbors get flagged as outliers.
So whether it's finding those hidden customer segments, prepping data by reducing dimensions, or spotting that one fraudulent transaction, UL is really about making sense of the unknown.
It absolutely is. It's often that crucial first pass over complex, unlabeled data. It helps us see the inherent shapes and structures hidden within. And yeah, evaluating it objectively is hard without labels, but the insights and the ability to simplify complex data make these methods indispensable tools for any data scientist.
And that brings us nicely to a final thought for you to take away. Given how tricky it is to measure accuracy in UL without labels, maybe the future isn't about striving for perfect statistical scores. Maybe it's about finding better ways to measure the actual usefulness or the discoverability of the patterns found.
Fitness for purpose.
Exactly. Think about it. In situations where you have zero prior knowledge, perhaps discovering any useful structure, any insight that leads to a good business decision, even if it's not perfectly clustered by some mathematical standard, is actually more valuable than forcing the data into a predefined classification scheme that might miss the real novelty. Something to ponder.
A very important point. Focus on the value generated.
We'll leave you with that. Catch you next time for another deep dive.